Welcome to section 1.4. Section 1.4 is going to be talking a little bit about some of the applications of integrals, especially to the theme of net change. So without further ado, let's take a look at an example. Example 1 says that to get to class every day, you walk in a straight line from your house to class. Today you make it 200 feet before you realize you forgot your textbook. You walk back home, leave for class again, and you get 100 feet before you realize you forgot your pen. All of your supplies in hand, you walk the 1,000 feet to class. What is your total distance traveled? What is your net displacement? So the main theme of this question is just to describe the difference here between distance and displacement. So if we draw a little picture of what's going on here, you have your house at one point, and you have class at some other point. And first you walk 200 feet, and you realize you forgot your textbook, and you walk back 200 feet, and then you leave for class again. But this time you get 100 feet before you have to walk back again, so another 100 feet back, and then finally you go 1,000 feet to class. So the total distance traveled here includes both the forwards and the backwards direction here. If we think of moving to the right as the positive direction, both the travel towards class and the travel away from class counts towards total distance. So total distance here includes the 200 feet that you walked at first, plus the 200 feet that you had to walk back home, plus the 100 feet that you walked to class, plus the 100 feet that you had to walk back home, plus the 1,000 feet that you had to walk to class, and now we are left with, looks like 1,600 feet. So you traveled 1,600 feet in total, but to talk about net displacement, what we're referring to with net displacement is just the difference between your starting and your ending values. We know that for this example, your house is 1,000 feet away from your class, and so the difference between the start and the end is simply 1,000 feet. Note that we could have thought about this 1,000 feet as treating distances moving towards class as positive and distances moving away from class as negative. So in addition to thinking about this just as the difference between the starting and the ending point, we could view this 1,000 here as 200 feet towards class minus 200 feet away from class, plus 100 feet towards class, minus 100 feet away from class, plus the 1,000 feet to class. So the reason that I'm bringing up this kind of second way of thinking about it here is that it's similar to what we've seen with definite integrals so far, where we're counting some areas as positive and other areas as negative. And that's exactly the connection that we want to make here. This displacement is going to be represented by a definite integral, whereas distance isn't quite going to be as nice. So let's get into a definition here. If the position of an object as a function of time is represented by s of t, the net displacement of an object between times t equals a and t equals b is going to be s of b minus s of a. So here we're just looking at the difference between the starting and the ending point. So to do an example here, a particle is traveling along an axis with velocity function given by 2 over t cubed minus square root of t plus 1. And we want to know what the particle's net displacement is between the times of t equals 1 and t equals 4. So we know net displacement here is going to be s of 4 minus s of 1. And it would be really nice if we had some information about the function s, but we don't. Instead, we know something about v of t, the velocity. And we remember from Calc 1 that v of t is the derivative of s of t. Velocity is the derivative of your position function. It's the rate of change in your position. So here what we might notice is that this is exactly saying that velocity, or rather position, is an antiderivative of velocity. What it means for position to be an antiderivative of velocity is that the position is that if we want to talk about this quantity here, s of 4 minus s of 1, we can think about that as the integral from 1 to 4 of of v of t dt. This is our fundamental theorem of calculus coming into play here. When we want to integrate some function, we can find an antiderivative and evaluate it at both endpoints and subtract. So here, now that I have turned the answer that I'm looking for into something that I know how to compute, we can actually go ahead and do the computation. Integral from 1 to 4 of 2 over t cubed minus square root of t plus 1 dt. So here we think back to actually doing this antiderivative, and it looks difficult. There are certainly some things that we haven't encountered before. We have a denominator here that has a t in it. We have a square root, and it doesn't look like we know how to do these antiderivatives right now. But if we change the problem into something that we do know how to do, we'll be in better shape. So I want to think about that t cubed in the denominator as instead being a t to the minus third in the numerator, because I know how to compute integrals of power functions, of t to some power. And so if I can treat this as t to some power, I may as well. I have a similar strategy for the square root. So I know that the square root is t to the 1/2 power. And now I want to apply some of my properties of antiderivatives to actually compute this antiderivative here. So I know that I can apply the integral to each piece of the sum. So integral from 1 to 4 of 2t to the minus third minus integral from 1 to 4 of t to the 1/2 plus integral from 1 to 4 of 1. Oh, we need a dt on all of these. And now I can compute some antiderivatives. So I know that I know that constant multiples stick around when I'm taking an antiderivative by my constant multiple rule. I also know that when I'm integrating a power, I increase the exponent by 1. So note that increasing minus 3 by 1 gets me up to minus 2 here. I have to divide by the new exponent. And let's see, so now I've integrated that function and I'm evaluating from 1 to 4. Let's see, increasing the exponent 1/2 by 1 gets me up to t to the 3/2, and I have to divide by the new exponent there and evaluate from 1 to 4. Integrating 1, I know that an antiderivative of 1 is t. Again, evaluated from 1 to 4. And so we go through this computation, and we get to, we want to plug in 4. So let's see, the 2 and the minus 2 cancel, leaving me with a minus 1. So I have minus, let's see, I have minus 4 to the minus 2. And I want to subtract away the function evaluated at 1. So that is minus 1 to the minus 2. Subtract. Let's see, I want to evaluate at 4, so that looks like 4 to the 3/2 over 3/2. Subtract away the function evaluated at 1, 1 to the 3/2 over 3/2. And finally, I want to add t evaluated at 4 minus t evaluated at 1. And if you work through all of these computations in your calculator, you should get around minus 0.6. So what exactly does this tell us? Well, it tells me that my particle has traveled to the left about 0.6 units. So geometrically, kind of what's going on here, what kind of picture do we have? If I want to draw the graph of v of t, maybe I have, I'm looking at it between times t equals 1 and 4. And at the very beginning, v of t is positive. If we plug in something like t equals 1, we find that v of t is around 1. And at the end, around t equals 4, we get something negative. We get something around -1. And so we find that the net displacement here we can find by finding the area under this curve, or rather the area between the curve and the axis. And so what's happening is the particle is moving to the right when the velocity is positive, and it's moving to the left when the velocity is negative. So this area here represents the total distance to the right. This area here represents the total distance to the left. And without an integral, you might know, well, the particle is traveling to the right for a bit, and then it travels to the left for a bit, but you don't know whether it ends up to the left or to the right of its starting position. Now that we have this integral available to us, and we can actually count this area, we know that the particle is going to end up a little bit to the left of its starting position, about 0.6 of a unit. So we do get a little bit out of having this integral available to us. All right, so let's move on and actually state this formally. This is called the net change theorem, and it looks a lot like the fundamental theorem of calculus because it essentially is. So if f of x is a differentiable function on the interval from a to b, then f of b minus f of a is the integral from a to b. So here we're thinking about big F as the antiderivative again, and there's a question of what's it an antiderivative of? Well, it's an antiderivative of its derivative. So f of b minus f of a is the integral from a to b of f prime of x dx. Another way of writing this would be to, well, we could add f of a to both sides. So we could think about this as f of b is f of a plus integral from a to b of f prime of x dx. So there's a question of why did we state it both ways, and it's because each way has kind of a different interpretation here. So A and B, so the interpretation of A here is that the net change in a quantity, so that's what this f of b minus f of a represents. It represents some net change, is the integral of the rate of change. So this is a nice way of thinking about how much in total does a quantity change. Well, if you know its rate of change, then you integrate. Part B, or the second part of this statement, says that the final value of a quantity, so that is this f of b here, we're thinking about that as the final value, is going to be the starting value plus the integral of the rate of change. So if we want to know what some value is at some point, and we know something about where it starts, and we know something about how it changes, then we can add that starting value to the integral of the rate of change. So example 3 is asking us, or giving us some situation here. It says if the rate of change in the number of people infected by COVID-19 in a geographic region t days after the beginning of the outbreak is r of t equals 0.5 e to the t minus 0.5, 100 people per day, how many new infections will occur between 1 and 3 days after the start of the outbreak? So the first thing that I want to call your attention to here is that this is not a real model. I made this up for the purpose of having a nice example to work with that's also a little bit relevant to what's going on right now. It really just is intended to indicate how calculus aids with the modeling process, rather than being some kind of actual predictive models. So these numbers here are certainly not accurate for any region, just made them up for the purposes of this example. So let's think about what we want to do here. We want to compute the number of new infections between 1 and 3 days. Well, the number of new infections between 1 and 3 days that's exactly what it means to be the net change in infections in number of total infections. And we have this nice theorem, the net change theorem, which tells us exactly how to compute the net change in the total number of infections. It says integrate the rate of change in the number of infections. So we're looking at the number of infections between 1 and 3 days, so I'm integrating from 1 to 3 here. I want to integrate the rate of change function, and we are told that the rate of change is this r of t equals 0.5 e to the t minus 0.5. So 0.5 e to the t minus 0.5 is the function that we want to integrate here. We can apply our usual integral rules. Now, I know I'm going to end up splitting up this integral into each of these pieces here because I have a sum, so I can just integrate each one of them separately. I know that the integral of e to the t is e to the t, so I get 0.5 e to the t as the integral of the first term. For the integral of the second term, well, the integral of 0.5 is 0.5t. So I have this function. I want to evaluate it from 1 to 3. And if I plug in 3, so I get 0.5 e cubed minus 0.5 times 3. And then I want to subtract away the function evaluated at 1, so 0.5 e minus 0.5. And you do a little bit of work and you plug this into your calculator and you get around 7.68. Now, this number has some kind of context. It certainly has some kind of units associated with it. If we want to think about what the units are, we might want to think, okay, well, the number of new infections here is the thing that we're computing, so this really should be some number of people. Note, however, that the rate of change is given in terms of hundreds of people per day. So this 7.68 here represents a number of hundreds of people. So this is 7.6800 people. And so we're looking at around 768 new infections. So more generally, you might want to know, how do I compute the units of some integral that I've computed? And remembering that integrals represent areas, you might think, well, it's the units of the input times the units of the output. And in fact, you would be correct. So units on f of x, on the integral of f of x dx, are the units of f of x times the units of x. So again, this should work nicely with your intuition from derivatives, where we said that the units on a derivative are the units of the input of the units of the output divided by the units of the input. Since integrals work in the other direction as derivatives, it should make sense that we have units of output times units of input.